Alright, today we'll be looking at some examples of sets and things we learned from the section from the couple lectures ago. And so let's take a look at this example. Alright, so the first thing we notice is we have four different separate sets with their corresponding elements. And so a good thing to do, and if you can't see the pattern, is you rewrite these sets. And so what are we gonna do to solve this problem, to know which sets are equal? Well, we rewrite our sets in order of alphabetical order. So as you can see, I did right here. And so what do we call this? We call this the axiom of extension, right? We could rewrite any of the elements any order. We could have repeating elements. We could that's about it. So two things: they could have repeating elements, and the elements could be in any order, and the sets will be the same. And so we're able to rearrange the elements if we want to. So that's just from our axiom, and I'm gonna write out how to spell that right now. Just let me finish this. And so I have two options right now. I could keep writing out the corresponding elements, or I could just write out the elements that are right here. So I'll show you right now what I mean. So for the sake of this example, I'll keep writing out all these elements. So this is how it looks like when I wrote it all in order. It's supposed to be C, comma D. So you can take it into steps too if you don't really know what you're doing. So let's see right here. So let's say I knew what I was doing already. I could skip that step and just write out what I need to write, because by the axiom, the definition of our axiom is like I just said right now, we could switch the order of how the elements are. The elements don't matter if they're equivalent, and we could eliminate the amount of elements because they mean the same thing. So let me post this right here, and I'll write out what I'm saying, what I'm using. So I'm using the axiom. You see that? That's how you spell axiom of extension. And if you don't know what this is, you should look it up or watch my video, because this is really important. So this is how you spell it. Just making sure I spell it right. See? Yeah, I spelled it right. So this is how you spell it. And like I said, we don't necessarily need all these elements. So I eliminated this one, and I eliminated that one. So now all we gotta do is compare which elements are which. So this says A, B, C, and D. This says A, B, C, and D. So we know these ones match. This says A, C, D, and E. This says A, C, D, and E. So we know these ones match. And so what do you think the answer is going to be? Well, just don't make it that complicated. Just say A equals C, they're equivalent, and B equals D. So that's a sufficient enough answer for this question. Alright, so here we go. Here's our next example. It says, write in words how to read each of the following out loud. And so first things first, what do we know about this? Well, we know that this is in set builder notation. So there we have set builder notation, and we have set, so I'll keep writing here, roster notation, right? And so this is really important, and we're going to define this right now. So what is this? This is set builder notation. Set roster notation is just simply the elements contained within the set. So this is set roster. Set builder notation, on the other hand, so set builder notation is defining a statement. So this is a statement right here. Symbolic statement. This is just basically the words of saying it. This is one way you could think about it. So this is how you say it. The words to say this is the set of the certain elements. Well, this is saying something else, and we're going to explain how to write this out. So let's take a look at our first example. And so I'm going to do this first. I'm going to do a couple examples with you guys. And so how do we read this? How do we start it off? We need to start off by within the brackets. And so we already know it's a set, right? Because we know that these brackets mean sets, the ones over here. I hope you can see that I'm making a circle here. So we have X, and I'm going to use E for elements right now because I'm typing. And so X is an element. So X is an element. That's how we started off. When you see the E right here, or the element sign, you see the symbolic one? We went over it before. It means is an element. Sometimes you could just read it as n is n, depending on the kind of statement, because it could be read self-explanatory. And if you know what self-explanatory means, it means you already know it. Like if you know math, then you would know what people are talking about. So that's the best way I can explain that to you. So is an element of the set. So right, because we're working with the set of all positive. And why is it positive? Because we have the little positive sign right there on top of this symbol, which is all positive real numbers. And when you're working with these symbols, which I explained the other time, the first video for this section, I explained that we could use superscripts, and the superscripts affect how the set plays out. So it's a set of all positive numbers, comma, and so why are we putting a comma? We're putting a comma because we're transitioning. We're transitioning to the end of our statement, which is saying where X is greater than. So this middle part's supposed to be X. I'm going to change it right now. Where X is greater than 0 and less than 1. So that's how we would answer this, and let me explain right now, more in depth. So this was supposed to be X. So it says X is an element, this is what it's saying at the beginning. X is an element of the set of all positive real numbers. And that's what it says in the beginning. And then the following part says comma, which is this part. Let me get a better color. Comma, where x is greater than, right? Because we have x right here. Greater than, x is greater than 0. You know it's written this other way right here. X is greater than 0 and less than 1. And there's no clear way to write this. I could have wrote this a whole different way, right? I could have said x is less than 1, then this and this, you know? You could, as long as it makes sense. This is just saying it this way because it might be easier. It sounds more fluent. But there's no clear-cut way to writing it, so this could be changed a little differently. And you could take out all right here of positive real numbers because it's limited to this. But this is what this is saying, all positive. So, you know, you could be subjective to what you want to write in it. But at the same time, you gotta still be objective into what you write into your statements. And so all that really meant when it says right now is that there's not a really wrong or right way to writing it, as long as you write what the statement's saying, which is where you're here, right? And so let's take a look. I'm gonna let you guys do this one at if you're at home, and I'm gonna just do the first part, the last part for you. It says where. So I'll do the last part right here for this problem, and all you have to do is do the first part. And if you are paying attention, you know that for the first part we don't need to write out the superscript. So this says where x is less than, so it's going to be less than or equal to, as you can see right here, x is less than or equal to 0. And feel anytime you want to stop the video and do the questions yourself, then go be my guest. And then when you catch up, just know that I'll be here to finish most of the problems. Of course, if you're really struggling and you want me to answer this part of the question, or not right here, this part of the question right here, I'm just gonna put it in a different color. Please leave a comment down below and I'll answer it. Or x is greater than or equal to 1. So it's going to be x is greater than or equal to 1. I'll just put it here. Alright, so now let's answer the next question. I'm going to answer this one, and I'll let you guys answer this one at home, the last one right here. And feel free to leave a comment if you're having a hard time or you want me to answer it. I don't want to take all your guys' time, so I'm only doing a select few. So this one says, so we gotta start it like how we started all the other ones. X is an element of the set, and let me expand this. And so you're gonna get a feel for what I'm talking about. So the set of all, and the z stands for integers, all integers. If it had a different negative sign, then it would be the set of all negative integers. If it had a positive sign, it'll be the set of all positive integers, right? So it's a set of all real integers. So you make sure you put real. Or you just leave it as integers. I don't think it really matters. That's what I mean. You could be kind of subjective in what you write out. It's a set of all integers where n is a factor of 6. And it's really that simple. And I guess I'll answer this part just so you guys could finish this. You won't leave a comment saying that you don't get it. So so I'm doing the last one here. X is an element of the set of all integers, and it's going to be all positive integers, where n is a factor of 6. Alright, so here's our next example, and let's see what happens. This is supposed to say equals, my bad. Let me erase that really quick. And so, if you want to pause the video and go ahead to answer these questions, then try it. So let's try this one. It says, is 4 equal to this? And that would be false, right? Because what's the problem with this question? 4 is the symbol 4, right? A number 4. And the other one is a set 4. And so you can't compare the set of 4 equivalent to the 4, right? They're both, you gotta take both these by what they mean, by their definitions. This is symbol / number. And this one is the set with an element whose number is 4. So I hope you get that. So now it says how many elements are in the set 3, 4, 3, 5. And if you remember the axiom of extension, right, I wrote it out over there. So I'm just going to put axiom. We remember that we don't need repeating elements, so that would be 3. So these next ones might be a little more complicated. It says how many elements are in the set. And so let's take a look. We know this is one element. We know that we could have another set within the set, so we know that's another element. So what's the problem with the next one? It looks really complicated, huh? It's a set within a set that has an ordered pair that has a set within the ordered pair. And so what do we know about ordered pairs? Remember, if you were to watch the other video, we know that ordered pairs can be indicated as elements, and they're sets in their own fashion. And if you guys don't know what I'm talking about, I'll make another video, and I'm hoping I'm making a video about some sort of historical presence in math, and I'll explain that in that video. But just know that that an ordered pair, if it's contained within a set, it's an element. So this is just one element. And so this is an ordered pair in its own way. So we know that this is one element. So what do we need to know? Let's see. 1. So we know this. So the problem that might be hard is trying to figure out why is this saying all this extra stuff on it. All these extra set notations with these brackets. And it doesn't matter, right? We gotta say this is take it as a whole. So this will count as one element, just like the ordered pair. So that's why I mentioned the ordered pair, because it's like an ordered pair. It's just one element. So that means this answer is only 3. I hope that makes sense to you guys. And if it doesn't, please leave a comment down below. I might make another video explaining this if you're having a hard time. Alright, right here it says the set of 0 is the set of 0 an element contained in this set. And if you're paying attention with over here, we know that this is true. So this is true. Why? Because this is an element within the set, and this is an element within this set. Sorry about that. This is a whole thing. It's an element. This whole thing's an element. Alright, let's look at the one right here. It says 0 is 0 an element within this, contained within this set, and it's false. Why? Because, and you, depending on who's your professor, you might want to explain why, or they might not ask you. So this is just saying 0, and this is saying just like how I explained it up there. So except now we're explaining it as elements. So this is the symbol 0 / number 0. It's not an element. In order to be an element, you need to be contained within the set. So if 0 was contained within the set, it will be an element, right? But it's not an element, so it's not contained within the set. Because this set, and 0 could be an element. Let me retract my words for a second. 0 can be an element if the set has 0 within it, right? If the set said this, then this would be true. But the set right here says the set of this. So this is one element, and this is one element but not within the set. And it could be, you could argue it's not an element at all because it's not contained in any set. So that's a whole different story. Our next example says, which of the following sets are equal? So this says the set of 0, 1, and 2. And this next one says, and so how can we tell what this one's saying? Well, it's read as x is all real numbers, such that, and right here it's saying -1 is less than or equal to x less than 3. So the problem is that there's a couple ways we could approach this, and sometimes the best ways are the most trivial ways. So right now I'm going to draw a line diagram here so you can see what I'm talking about. And so we know that less than or equal to means a closed circle. We know less than just means an open circle. So this is how this is going to look like. The problem is that this is probably might take you longer. It's a longer approach. And so right here we have -1 again. And these are all open circles. And these are all real numbers. And what do we know about real numbers? They contain all numbers. And so right here, this is defined at -1. Well, this is defined at point -999, etc. and so forth. So that's how it's read, and so forth. And so right here, this one says x is in, or x contains the elements of z, which are integers, such that -1 is less than x and less than 3. And so what do we know about this? What do we know about integers? We know that this is how integers work. And so, and what is that called? And so forth. Okay. And 0, -1, and so forth. And those things are called, we emphasized it last time, ellipses. Right, ellipses. And so, really important. Well, important for sets mostly, because this is the set of all integers, all real integers. And so, what do we know about this? We know it can't be -1 because in order to be -1, it has to be defined at -1, and it's not defined because it's not less than or equal to. So the only things that can be in between here are 0, 1, and 2, and that looks a lot like A. So we know that these are matched together. And so let's look at the last one here. Maybe we could match this up. And so this says all positive integers. And so what does that mean? So we gotta go like this, 1, 2, 3, and so forth, or and so on. And it means the same thing. So we got this. And so let's write them out. It says 1 and 2. And so which of the following sets are equal? If we were to take a look at our sets, we would know that only D and A are equal. So we say A equals D, and that just means set A is equal to set D, and that's our answer. Alright, let's take a look at this next example. It says for each integer n, let Tn equal the set of n, that's supposed to be a comma, my bad, the set of n squared, so it looks like that, right? How many elements are in each of T? This is a subscript 2, T the subscript of -3, or you could read it at T sub 2, T sub -3, T sub 1, and T sub 0. And let's not get caught up on how to say this. Let's keep going. It says justify your answer. And so, what do you guys remember from one of the examples we did? And I think some of the examples like this we're not going to see as much if we're taking a test, but it's still something to take note about. All you gotta do is plug in your numbers in, right, because these stands for n, into our general set right here, or our function, and see what it gives us. So we plug in t squared, t sub 2 I mean, that's going to give us the set of 2, and what's n squared? 2, 4. And then we do our next one. It's going to be, let me see, t sub -3, there you go, my bad. It's going to be -3, and -3 squared is going to be 9. So these all have their own individual elements. How many elements are in each of these? Okay, T1. Let's see. It might take me a while just because I'm looking at this. It's 1 squared, so it's going to be 1. And T sub 0. And so what we're doing is we're just simply plugging in numbers into this function. And those numbers are, and I use a different color. Those numbers are right here. Plugging these numbers in to to this function. So let's keep going. Last one says 0. And so we got to be familiar with their axiom, right? And that's the axiom of extension. And so this all means the same thing. So we could say that this just means, and this just means, t sub 1 means 1, a set of 1. That's his element. T sub 0 means 0. Alright, so how many elements are in each of these? This has 2 elements. This has 1 element, right? This has 2 elements. This has 1 element. And so if we add up all the elements, so that's be 2, 4, 5, 6. And so that just means we have 6 elements. A grand total of 6 elements. So you can say 6 elements. And the question is just asking in general how many elements are contained in this specific set. And so t sub n just means set. And so it says justify or say how many elements are in each. So they're saying how many elements are in each of these individual sets. So we don't really have to write that out. Alright, next one is use the set roster notation to indicate the elements in each of the following sets. And so this is the set of S, which is going to be N. So N right here, which is in this. And let's see this go. So mostly all we need to know is plugging integers for k. So we're going to plug in integers for k, we're going to plug in the min for our function. So this would say n is a, so just so you guys can understand a little more, n is a element of the set of all integers. And you could say it different ways too. Just don't get caught up in how to say it. And most of the time I say such that n equals this. You could say comma where this equals this. You know, don't get caught up in how to say it. Be creative in the way you say things. So then we go over here. So all this is, these 2 questions are asking is, we plug in integers for k and we're trying to find out how many elements are contained in this. If it's infinite elements, then we'll just say that the set is infinite. The set has no boundaries. Or you say the set, you can say a lot of different things, you know. So that's all we're going to do. So we're going to plug in numbers for k. Let's say I plug in 1 for this. What would I get? And if you have a hard time seeing it right here, here's the function. If I plug in 1, and if you guys don't believe me, then plug in more numbers in. So it's going to say, and it's not supposed to have x, so sorry about that. You get confused. Let me see. So it's just supposed to say -1k. So you just plug in numbers for k. Let's say I plugged in 1. What would it be? It would be -1. Let's say I plug in 2. What would it be? And so I hope you're following what's happening. So if it's squared, it would be -1 times itself, right? Because that's what squared means. And so that's going to give us 1. If it's 3, it's -1 times -1 times -1. and that's a negative number. And so we don't have to write out repeating elements, because we're using our axiom of extension. And the axiom of extension says we don't need to keep writing out repeating elements, and it also says that it doesn't matter the order of how you write our set. So this will be your answer. And I hope you guys are following me. And I'll give you some time to try to solve this, the bottom one right there. And if you're having a hard time, I mean, the best thing I could tell you is that it's just simple math, and all you need to really do is plug in numbers for the function. So let me go solve it for right now. So this is saying I, and you just gotta plug in integers, right, into I. And so like we did earlier over there, let's say I plugged in 1 into our function. And take note that this is contained within a set, right? This is contained within the set. You can see right there. So even though this is a function, this function's contained within the set. And so when we solve the function, it gives us a certain element that's within the set. And so you could think as the function as an element. So let's carry on right here. So 1 plus -1, and in this case it's going to be I instead of K. Let's say I plug in 1 in here. What would happen? We would get 0. I hope you guys can see that, because -1 plus 1 is 0. And we plug in 2 for I, right? We square it. -1 times -1 is positive. 1 plus 1 equals 2. And so that's all it's going to be our answer. This is 2 elements. So it says use set roster notation. You know what set roster notation is? It's just using this and having elements within it to indicate the elements in each of the following sets. So that's your answer, and I hope that helps. So let's go to the next problem. Here's our last example. It says, is 3 an element of 1, 2, and 3? So let's take a look. So is 3 an element of our set right here? And the answer is clearly yes, right? Because this is an element. But also is asking, is 3 an element contained in here? The answer is yes. You can put yes or true. I'm just going to put T for true. This one says, is the set of 2 an element contained in this set? And the answer is false, right? Because in order for this answer to be true, then the following set B, so I'll denote this as set B, as this is set A. Following set B needs to say that this set's an element. So you can see right here that this is not an element in here. This isn't. If A was a set element right here, then this would be true, but it is not. So that's false. So let's continue on to our next question. It says, is 1 an element in this set? And the answer is true. And why is that true? Because 1, remember like I said right here, is an element, and this is an element. Alright, so let's go. Let's answer this first. So what does it mean to be a proper subset? So the second one right here, C, says, I'm going to put prop, which means proper subset. Or at least I'm simplifying it. And so what does that mean to be a proper subset? So proper, so I'll write it out for you guys. The definition of proper subset says the proper subset of B if and only if every element of A is in B, but there is at least one element of B that is not in A. So that's the definition of proper subset. And so, do we have a proper subset? Well, if this was so this is just an element. But let's say, let me change up this question. Just so we could know what a proper subset is. Because we're going to go on and we're going to find one. So I was mistaken when I said that. But this means proper subset. And so, this is proper subset. Because it says right here, set A. So I'm going to denote this as set A. And this is set B. And there's at least one element, right here, element, that is not in the corresponding element A. And so that's what it means to be a proper subset. And this is a set too, right? So let's go in here. This is a proper subset. Why? Because it has 1. And this has the element 1. So a set has an element 1. The following set has element 1. And this is true for the answer, right? And it's a proper subset. So I'm going to put prop. Alright, next one says, is the set 1 a subset? The set 1 containing the element 1 a subset of the set containing the elements 1 and the element of the set of 2? And that is true. Is 1 A, and what does it say? Subset of the set 1? And so this is false. Why is that false? Well, 1 is not a set, right? In order to be a subset, first you need to be a set. And so this 1 is not even a set. And I hope you're following what I'm saying. If it said this, 1 is a set. But since it doesn't say that, 1 is not even a set. And if it said, is 1 an element within this, then that would be true, right? But is asking us, if the question is asking us, is 1 a set that's contained in here? And that's false. So our next one says, this is set of 3 an element of the set of 1, comma the set of 2, comma the set of 3. And so let's understand what this question is asking. It says this is an element, this whole entire thing is an element, and this whole entire thing is an element. So this is true. Alright, this one says, is the subset of 2, which means we're only looking at, is the set of 2 a set contained within 1, comma, the set of 2, comma, set of 3. So, think about it. When we're talking about subsets, we're only talking about the elements within our sets. And so, if we're only talking about the elements within our sets, then we're only talking about 2 for this. If we're only talking about elements in our set, then we're talking about 1, and this thing as a whole, right? We're talking about this as a whole element. whole entire set's an element, and a whole entire set's an element. And so that'll be false, because when we're talking about subsets, we're only talking about the elements contained within the set. And so this one says 1 is an element contained within here. And everyone knows that would be false, because 1 is an element. Let's say it's asking that 1 is an element right here, and this is a whole element, so that'd be false. It says is a subset 1 a subset of 1, and so that answer would be true. And so that would be our answers. And so this would be a subset of itself. And so that's one of the other interesting things about sets. A set can be a subset of itself. Really important. It might be asked on a test. Sometimes people ask, can a set be a subset of itself? And the answer is yes. And the other question is, a set can contain a set within itself. A set can contain a set within itself as an element. And then you can see what I'm talking about right now. As an element. So that's another important thing to take note. And what does that mean? It means that, let's say I had this set right here containing 1 and 2. Then if this was a set, then this set, let's say I denote this set as set C. Our set C contains a set within itself as an element, because this is taken as a whole element. And what is the other interesting thing we could take out of this? All these questions. So we learned a set can be a subset of itself. A set can contain a set within itself as an element. A proper subset of B is when it contains one less element. So let's take a look. That's the one I was just thinking about which one to explain. So when we are talking about subsets, we are talking about the elements contained within the set. And so I'll explain that one right now. So let's say we're talking about example here. Let me think of one. Let's say I had 2. Let's set 2, and we're looking at this subset, and we're going to say we have 1, and let's say we had 2, and we have the subset of 2 as an element. And so what is this saying? It says we are taking when we're talking about subsets, we're talking about the elements contained within the sets. And so then you change this color. This is one element, right? This is one element. This is one element. This is one element. And so we're only talking about this and this. The elements contained within the set. And like I said, a set can contain a set within itself as an element. And so those are 4 things we need to take note if you're new to this kind of stuff. And so I highly suggest, if you're new to this, write this down. If you're a pro at this, then you didn't really need to, you probably could have skipped this part. So let's go on to the next question. Alright, so we're going to do this question. And before that, I want to say, if you already know how to do this, then stop the video and do it yourself. And after you finish this problem, I want you guys to do these problems at home and post it down below for the comments. See if you get it right. It'd be interesting to see what your guys' answers are. And it's not for practice for yourself, you know. I already did most of the work for you guys. So let's see right here. So it says S cross T. So that's how you read it. S cross T. And these are called Cartesian products. So I'm gonna write that out for you guys. Cartesian and products. And they're all capitals, so, right, because this is definition slash way of doing this. So Cartesian products. So all we're gonna do, and so before this, I'm gonna give you a pro tip. So if we're asked to find a Cartesian product, we count the number of elements within our set. So there's 1, 2, 3. And then we count the numbers within the other set. 1, 2, 3. And we grab the biggest number, which is going to be 3, and times, what's the biggest number over here? 3. And that ends up giving us, what do you think that gives us? The number of elements. So that's a pro tip, right? But the problem is with this strategy is sometimes you could have the same elements repeat. And let's say let's say I'm gonna do an easy one for you guys before we get on to this big one. Let's say we had 2, 2 as one set, and t equals 2, 2. So this is a pro tip, only works when you know that all the elements are different. Because if the elements are repeating itself, then you could mess up. And I don't know, I can't give a good specific example. I'm not even sure if this is actual proof. If it's not, then I might prove it later to show you guys. Maybe it'd be a nice proof if people haven't wrote a proof about it yet. But pretty sure someone has, and so let's see right here. 2, 2, t equals 2, 2. So we multiply them in. It's like just like basic multiplication. So we multiply 2 by 2 by 2, and we get 2, 2. And if you know what the answers are going to be, and by the way, this is going to be in order pairs. So we're going to have 4 order pairs that say the same exact thing. And what do we know about our axiom? So I'm just going to write out 2. We know that if the numbers repeat themselves, then they don't count. You're saying the same exact thing. That's what our axiom of extension says. And so what happens is we're only going to have one element. And so this is a pro tip, right? And if you guys wanted to, you could go back and pause it and write this one down, because this is a really good example, the one I just did right now. And this pro tip works only if you have different elements. And I'm not sure, like I said, I might do a proof later of doing this, and it'll be fun. It'll be a fun video to watch once we get through this course. But before that, just know that this won't work all the time. And that's why it says write them all out. Once we get better, we'll figure that out. So now we're just gonna multiply all them out. And so now we're doing it the long way. This is why I told you guys could solve these two at home and post them. I might even just do one because, you know, it just takes too long. Feel free to fast forward if you like, because I know if I was in your shoes, yeah, I wouldn't want to watch this. But, you know, everyone's entitled to their own opinions and their own thoughts. The only reason I would watch is because I always have some kind of commentary to say. Something funny, I don't know. I'm not a funny guy. So you just see, this is why I don't like this kind of problems. This is something I mean, it's something easy to put on a test, right? I mean, you hope your instructor puts it on a test. That is just something that, you know, it's pretty much common sense and a waste of time. After doing like 4 of these problems, you'll be like, okay, this is too easy. The problem is they're going to be harder. It's the ones that we did earlier, where you had to write them out, or the elements contained within a set. Those are a little harder, you know. And so right here, you know, we have 9 elements. Just like I said, we did our pro tip. So I'm going to put 9 elements back here. You already know that. And so we have, before that, you could get it wrong if you don't put it into set roster notation, as it's seen right here, right? So let's say if I left it like that, I would have got it wrong. So you got to put these little brackets. And so we do this next one, and always just start with your brackets, you know. Maybe they'll cut you the slack if you forget to put your bracket over here. I mean, I would cut you some slack because this is just a tedious problem. And so let's see what we're going to do right here. Our next one says 2. And so you got to multiply it by itself. And at the same time, I don't know. It depends where you're at. Some professors might not cut you any slack because, you know, if you forget notation, you messes up the whole entire thing. You mess up your proof. You mess up, especially if you're a mathematician or something. You're writing proofs. That's a big problem. That's a no-no. And so let's see right here. Keep going. Told you this takes forever. Might be a little faster with the pencil. And that's why I told you the pro tip right now, because if the question's not indicating, it's just asking you how many elements are there, then you just don't need to worry about it. Of course, if you make a lot of mistakes and you don't want to mess up, then you might want to do the whole thing. And so that's our answer, and that's 9 elements. And I'll leave these 2 problems up to you. So this is t times t and s times s. And if you don't want to do it, you don't have to do it. It's just something simple to get the hang of it. And these are Cartesian products. You always want to put them in set roster notation. And that's about it. And hopefully later on I could prove this to you. Why a certain n number and some kind of n number and a repetition. And I don't know, I'm just thinking about it. It sounds like something interesting to do. And maybe I'll make a video about it later. So thanks guys for watching, and I hope I can see you guys next time. If you have any ideas of what you want to see in the future, then please let me know. If you want to see more problems like this, you're having a hard time, please let me know. If you're having a hard time at a specific area, then please let me know. I'll make a whole entire section of video for that, maybe a 10-minute video or 5-minute video, however long you think is. Just leave the amount of time you want, how long the video, I can make it that long. And the reason why these videos are so long is because I take my time to explain it to you guys, and I take my time showing you examples like these. And if you are done this class before and you want to see something else, something more specific, then please let me know. Or if you haven't done this class and you're a little bit you don't want to see this section and you want to do sections on proofs, please let me know that too. And thanks guys for everything. I'm hoping also to make a video where I talk about math and some kind of philosophies too. So if you're looking forward for something like that, please let me leave a comment down below in the description. And please subscribe and like this video because it will help my channel grow, and I really need this channel to grow to continue making these videos, because it takes a lot of time to make these videos. It took me a couple hours to make this video, plus the whole day to record, and now I needed to edit it. So just let me know for ahead of time if you guys want to see anything specific, so I don't have to spend the specific time doing stuff like this. So thank you and goodbye.